We're in Chapter 11, Infinite Sequences in Series Part 1. Section 11.1 deals with sequences. So a sequence is a list of numbers written in a definite order. So we're going to call this a sub 1, a sub 2, a sub 3, and so on, where a sub 1 is the first term, a sub 2 is the second term, and in general, a sub n is going to be the nth term. Note, for every positive integer n, there is a corresponding number a sub n. Thus, a sequence can be defined as a function whose domain is a set of all positive integers. Notation for an infinite sequence is defined as, and we have braces a sub n or a sub n from n equals 1 to infinity. First example on here says to list the first 5 terms of the sequence. So in order to do this, we need to find a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. And so in order to do this, this means that n, the value that we have, is that little value that we have with a. So for the first value, n is equal to 1, our subscript. So we have 3 to the first over 1 plus 2 to the first. And working this out, we get 3 over 3, which is just 1. A sub 2 is going to be 3 to the second over 1 plus 2 to the second, which works out to be 9 over 5. A sub 3 is going to be 3 to the third over 1 plus 2 to the third, which works out to being 3. A to the fourth we get is 3 to the fourth over 1 plus 2 to the fourth, which works out to being 81 over 17. And then the fifth term that we have is going to be 3 to the fifth over 1 plus 2 to the fifth, which works out to being 81 over 11. We can then list these in order, so a sub 1, comma a sub 2, comma a sub 3, so 1, comma 9 over 5, comma 3, comma 81 over 17, comma 81 over 11, and I'm going to go ahead and put comma dot 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 because we could continue this on and find additional terms. So we're going to do exactly the same thing for our next sequence, so a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. So again, a sub 1, we substitute in values of n is 1, and so we have negative 1 to the first times 1 over 1 factorial plus 1. And so this is going to simplify to negative 1/2. The next one that we have is going to be negative 1 to the second times 2 over 2 factorial plus 1, which works out to being 2/3. So next we're going to try to do the next 3 terms on your own and to work those out. So the next 3 terms that you should get when you simplify it, it's going to be negative 3 over 7, 4 over 25, and negative 5 over 121. Also note that, remember that the factorial means, so 5 factorial means 5 times 4 times 3 times 2 times 1. Likewise, 4 factorial is 4 times 3 times 2 times 1. And so writing those lists that we have, our sequence in order, we get negative 1/2, comma 2/3, comma negative 3/7, comma 4 over 25, and negative 5 over 121. This is an alternating sequence. It's going from negative to positive, negative, positive, and negative. So the next one that we have is done a little bit different. This one tells us that we have a sub 1 is 6. And then it tells us that our next term is found by taking a sub n, which is the previous term, divided by n. So a sub 2 is going to be a sub 1 all over 1, since that's our n value. So we get 6 over 1, which is 6. Then a sub 3 is going to be a sub 2 all over 2, which is going to work out to being 6 over 2, which is 3. A sub 4 is going to be a sub 3 all over 3, which works out to being 3 over 3, which is equal to 1. And then our last term that we get is a sub 5, which is going to be a sub 4 all over 4, which equals 1 over 4. And so listing these values, we get 6, comma 3, comma 1, comma 1/4. And again, put dot 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 saying that this can go on forever. This is a recursive equation that we have. It relies on the previous term, or sometimes it might rely on more than just one term. And this is also our sequence that we would get. The next example has us going backwards, and it says find a formula for the general term a sub n of the sequence, assuming that the pattern of the first few terms continues. So this is our a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. And so we need to think of a way to write this so we can see that pattern. So I'm noticing that the numerator is always a 1, but it's alternating. And so add 1, then negative 1, then positive 1, then negative 1, then positive 1 up in the numerator. The denominator, I'm noticing that we have powers of 3. So this would be 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, and again so on. That first term though, I don't see a 3 in there, but if I were to rewrite this as 3 to the 0 power, which is just 1, that would be 1 over 1, which equals 1. And so our general formula that we would have, a sub n, would be equal to, and notice that since this is our a sub 1 term, a sub 2, a sub 3, and so on, that exponent is actually 1 less than what that term is. And so this is going to be 3 to the n minus 1 power. And likewise, like we saw up in part B in the example before, since this is alternating, I'm going to have a negative 1 raised to a power. So raising it to an odd power would give me a negative number, and an even power would give me a positive value. So the first term is opposite of what I just said, and I need it to be positive. So I'm going to go ahead and rewrite this as n to the first. A good idea here is to double check by substituting in 1 to see if you get a sub 1, subbing in 2 to see if you get a sub 2, subbing in 3, and seeing if you get a sub 3, and so on. You can rewrite this, since they have the same exponent, as negative 1 over 3 to the n minus 1 power. At the top of the next page, it says a sequence has a limit L, and we write the limit as n approaches infinity of a sub n equals L, or as a sub n approaches L, n approaches infinity, if we can make the term a sub n as close to L as we like by taking n sufficiently large. So if the limit as n approaches infinity of a sub n exists, we say the sequence is going to converge. And converging means that it is going to go to a specific value, so to a number. So it goes to a value. Otherwise, we say that the sequence is going to diverge. And again, this is talking about a sequence. A more precise definition is given. So a sequence a sub n has a limit L, then we write the limit as n approaches infinity of a sub n equals L. If for every epsilon greater than 0, there is a corresponding integer n such that if n is greater than n, then the absolute value of a sub n minus L is less than epsilon. So we have limit laws for sequences. And so for this it says if A and B are convergent sequences and C is a constant, then the limit as n approaches infinity of these can each be taken individually. So we can take the limit of A plus the limit of B. And likewise for subtracting, if we're multiplying a sequence by a constant, we can factor a constant out of it and then first evaluate the limit and then multiply by that constant. And then also note over here on this side that the limit as n approaches infinity of a constant is just a constant like we saw back in Calculus 1. And then if you're multiplying two sequences together, you can take the limit of each of those individually and then multiply it. Likewise, if you're dividing, you could take the limit of each of those, the numerator and the denominator separately, and then divide it. And again, this is provided that that limit as n approaches infinity of our denominator does not equal 0. And then if you are raising a sequence to a power, then we can take the limit of the sequence first and then raise it to the power. So right below this, we have a theorem. It says if the limit as n approaches infinity of f of x equals L, and f of x equals a sub n, where n is an integer, then the limit as n approaches infinity of a sub n is equal to L. The next little formula we have below that says the limit as n approaches infinity of 1 over n to the r is going to equal 0 if r is greater than 0. And then the next definition that we have says the limit as n approaches infinity of a sub n equals infinity means that for every possible number m, there is an integer n such that n is greater than n and a sub n is greater than m. I also want to remind you guys about two sequences that we saw probably back in Algebra 2. So one is the geometric sequence, and the other one is going to be an arithmetic sequence. And so with geometric sequences, this is where you are multiplying to go from term to term to term, and we had a common ratio. And so we had a sub n is equal to a sub 1 r to the n minus 1. And if you remember, this is going to converge if our r value is in between -1 and +1. And then we had an arithmetic sequences, which is where we were adding or subtracting to go from term to term to term. And so our formula was a sub n equals a sub 1 plus n minus 1 times d. So good things to remember. Might have forgot about these, but definitely things to look back on. So at the top of the next page, we talk about a special theorem. This is called the squeeze theorem. And the squeeze theorem states that a sub n is less than or equal to b sub n, which is less than or equal to c sub n. So our sequence b sub n is bounded by a sub n and c of n for n greater than or equal to n naught. So the limits of each of these, a sub n and c sub n, is what our sequence b sub n is bounded between. And those are both equal L. Then we can conclude that if it's both of those values, the limit as n approaches infinity of the sequence a sub n and c sub n both equal L. Therefore, they're squeezed between the limit as n approaches infinity of b sub n. It's squeezed between those two. It's also going to be approaching L. So sketching a little picture of this would be if we were dealing with a sequence, and as we're taking that sequence, it's approaching a value. We'll say this is n. So as we go out farther with our sequences, it's doing something, but those values are approaching a value. And we'll say this is our a sub n, since it's our smallest. And likewise, whatever's going on with our c of n, but it's also approaching that same value, then we can say that whatever b is doing, and I'll switch colors here, whatever b is doing, and I'll put dots, as that sequence goes on, it's also going to be going to L. So the theorem right below this says that if the limit as n approaches infinity of the absolute value of a sub n equals 0, then the limit as n approaches infinity of the sequence a sub n is also going to be equal to 0. The next theorem that we have says that if the limit as n approaches infinity of a sub n equals L and the function f is continuous at L, then the limit as n approaches infinity of our function of that sequence would just be equal to f of L. And then right below that we have another definition here that says the sequence r to the nth power is convergent if r is between -1 and 1 and divergent for all other values. So this ties into that geometric sequence like we saw before that we learned back in Algebra 2. And so for example, there's some space down here. For example, if I asked what is the limit as n approaches infinity of 1/2 to the nth power, and so since this is our r value, r is equal to 1/2, and that is in between -1 and 1, we can say that this limit is going to equal 0. Likewise, another example, if we have the limit as n approaches infinity of 1 raised to the nth power, we would say that r in this case is equal to 1, and when r is equal to 1, we get an answer of 1 for our limit. So right below this, the example says determine whether the sequence converges or diverges, and then if it converges, find its limit. So the first one, part A, says a sub n equals n to the third over n to the third plus 1. And so what we need to do is take the limit as n approaches infinity to determine if this is going to converge or diverge as it goes on. And our sequence is going to be n to the third over n to the third plus 1. And if you were to evaluate this as n approaches infinity, note that this would equal infinity over infinity, which we know is indeterminate. So back in Calculus 1, we learned that there was a few different ways to deal with this. One was one of the methods that we discussed back in pre-calculus. Another one was to multiply all the terms by 1 over the degree in the denominator. So the largest exponent that we have for this is to the third, and so I'm going to rewrite the limit as n approaches infinity of n to the third over n to the third plus 1, and I'm going to multiply both the top and the bottom by 1 over n to the third. You can also write it as just dividing every single term by n to the third, but we end up with the limit as n approaches infinity of, the numerator is just going to be n to the third over n to the third, which is 1, and then in the denominator, since this gets distributed to both, we have 1 plus 1 over n to the third. And then we remember from Calculus 1 that the limit as n approaches infinity of 1 over n to the third is just going to converge to 0. And so this is going to equal, if we take the limit of each term individually, we get 1 over 1 plus 0. Again, in the numerator it's 1, and then also in the denominator I have a 1, and taking the limit of a constant is just equal to that constant. And so this simplifies to just 1, and so this converges to a value. Looking at part B, it says a sub n equals n to the third over n plus 1. And so again, evaluating this as the limit as n approaches infinity of n to the third over n plus 1, we would get infinity over infinity, which is also indeterminate. And so exactly the same idea. So the limit as n approaches infinity of n to the third over n plus 1, multiply both the top and the bottom by 1 over n. And then doing this, have the limit as n approaches infinity of n to the third over n is going to become n squared over, and in the denominator we have to distribute this, and so we have 1 plus 1 over n, and this value of 1 over n is going to go to 0 as we take the limit of it, because 1 over something really, really big is going to be practically 0. But the issue we have here is going to be the numerator. So the numerator is actually infinity squared, which is also going to be an extremely large value, and we would say this is equal to infinity. And so what we would have is going to be infinity over 1 plus 0, which is just equal to infinity. And so it's not a numerical value, so we would say that this is going to diverge. The next example, part C, says a sub n equals 3 to the n plus 2 over 5 to the nth. And so dealing with this one, we're going to rewrite it a little bit different. But I'll go ahead and put the limit as n approaches infinity. So 3 to the n plus 2 over 5 to the n is going to be equal to, and I'm going to rewrite the numerator a little bit different. So this is 5 to the nth, and this is the same as saying 3 to the nth times 3 squared. If you remember your exponent rules from Algebra 1, if you have 3 to the n times 3 squared, since they have the same base, you're able to combine that together and add your exponents. So it's pretty much what you did is going backwards, and we took 3 to the n plus 2 and rewrote it as 3 to the n times 3 to the second. So from here, the 9 that I have is just a constant, this value here, and I can pull it out in front of my limit for my limit rules. And I have the limit as n approaches infinity of, and I'm left over with 3 to the n and 5 to the n. So I'm going to rewrite it as 3 over 5 to the nth exponent that we have. And since I have 3 over 5 here, this 3 over 5 is my r value, and r is equal to 3/5. And since it's in between -1 and 1, so since it's in between -1 and 1, we can say that this is going to equal 0. And so we have 9 times 0, which is just going to equal 0. And so this converges, since 0 is a value, it's a number. The example right next to this one is part D, and this one says a sub n equals the square root of n plus 1 over 9n plus 1. And so evaluating this as the limit as n approaches infinity would be infinity over infinity also. And so this is also indeterminate. And so in order to deal with this, I'm going to go ahead and rewrite this and say this is going to be the square root of the limit as n approaches infinity. Again, this is one of those rules when you had an exponent on that sequence of n plus 1 over 9n plus 1. And then, since it is indeterminate, I'm going to do exactly what we did on the first two and multiply by that degree that we have in the denominator, which is 1 over n to every single term that we have. So we have the square root of the limit as n approaches infinity of, and this 1 over n has to get distributed, so we end up with n times 1 over n, which is 1, plus 1 times 1 over n, which is 1 over n. And likewise, 9n times 1 over n is equal to 9. And then 1 times 1 over n is going to be 1 over n. And so these are both going to go to 0 as we take the limit. And so we end up with the square root of, when we evaluate the limit, of 1 plus 0 over 9 plus 0, or the square root of 1 over 9, which is going to be equal to 1/3. And so we'd say this also converges. Part E says a sub n equals e to the 2n over n plus 2. So we take the limit as n approaches infinity of e to the 2n over n plus 2. And so evaluating this, we would also end up with an exponent of infinity over infinity, which would be indeterminate. And so e to something that's indeterminate is also going to be indeterminate. We can't determine it. And so do exactly what we did on the previous problem, and the first two is multiplied by 1 over n, but up in the exponent. So we have the limit as n approaches infinity, and I'll make a little note here. This is because this was indeterminate. And our value is going to be e to the numerator is 2n times 1 over n, which is just 2, over 1 plus 2 over n. And then taking the limit, you are able to take the limit. E is just a constant, so we can rewrite this as e to the limit as n approaches infinity of 2 over 1 plus 2 to the nth, and this value of 2 over n will go to 0, and so we have e to the, evaluating the limit, it's going to be 2 over 1 plus 0, which equals e to the positive second, and this is an actual value, a number, and so we can say that this one converges. I'm going to go ahead and circle F and G, and we'll look at both of those in class together. So we're going to go ahead and look at H. H looks a little different. This one says a sub n equals the natural log of n squared over n. And so again, starting at the same way, we're going to find the limit as n approaches infinity of ln of n squared over n. And again, if we were to evaluate this as n approaches infinity, we would still end up with infinity over infinity, which is indeterminate. And another method that we had for dealing with indeterminate forms of infinity over infinity would be using L'Hopital's rule. And this is back in section 4.4 in our textbook. And so with this would have worked on the other problems that we had too and could have used L'Hopital's rule. So remember, there's always a lot of different ways to do this to make sure you show clear steps so that it's easy to follow along with what you chose, which method you chose to do the problem. Okay, so since we have this, it doesn't work using the method that we did on the first two or part D or even part E, just because if you were to multiply by 1 over n, it would clear up the denominator, but it doesn't do anything for the numerator since it's not a polynomial. And so I'm stuck, so I'm going to go ahead and use L'Hopital's rule. And so L'Hopital's rule, the limit stays exactly the same. And we're going to take the derivative of both the numerator and the denominator, but separately. So the numerator, taking the derivative of that, we have to use the chain rule. So we have 2 times ln of n times the derivative of ln of n, which is 1 over n. And then the derivative of the denominator, which is just n, is just going to be 1. And so from here, I'm able to pull the 2 out in front. So I have 2 times the limit as n approaches infinity of ln of n all over n, which if we were to evaluate this as n approaches infinity, this would still be infinity over infinity and we would still be in indeterminate form. And so we're going to go ahead and use L'Hopital's again. And notice I'm putting an LH above my equal sign when I'm using L'Hopital's. So this is a way to communicate that you are using L'Hopital's rule. So we still have a 2 out in front, and then a limit as n approaches infinity. Taking the derivative of the numerator, the derivative of ln of n is going to become 1 over n, and then the derivative of the denominator is just 1. So this simplifies to being 2 times the limit as n approaches infinity of 1 over n. And as n approaches infinity, 1 over n is going to equal 0. And so we have 0 times 2, which is going to be equal to 0. So this converges.